everybody. Welcome back to Measure Theoretic Probability. For the last few videos, we have been talking about extending a probability measure that is taking in sets in a field to the sigma field generated by the field. So we had a field called curly F naught, and it had a probability measure P that takes in sets in that field. And then we used curly F to denote the sigma field generated by curly F naught. So we're mostly there with the field. To get the full sigma field, we need to make sure to throw in all of the countable unions that might not be in there. We want to define a probability measure on the bigger field, curly F, and we want it to be an extension of the original measure in the sense that the new probability measure of a set in the original field needs to match the original P of A, the original probability measure in that field. Even just setting up the scenario and our definition of what we called an outer measure took a long time. We proved it, quote unquote, in the last video without proving a lot of sub-steps. There were lemmas that we needed to get to our goal. A lemma is just a theorem, but it's usually called a lemma if it supports another theorem or another result. We had 6 lemmas, and in the last video, I asked you to just assume they were true. And if they were true, we concluded that our P star, which was defined as an infimum of the total probabilities added up from sets that cover an original A, then we proved that that was in fact a probability measure when you considered the sigma field F without the naught, when you considered the sigma field F. So the point of this video is I want to prove those lemmas. I don't want to leave anything unproven, but it's optional. If you don't want to watch this, I would skip ahead, not to the next one, but to the one after that, where we get to limit sets. I also think that the lemmas in this video, we're going to do lemmas 1 through 3, and in the next video, 4 through 6. I think that the proofs are kind of not specialized. So I think that there is knowledge to be gained if you're not comfortable with proofs by going through these, and that steps that you might take in other proofs, as opposed to something really specialized that I'm just proving this one thing and I'll never use this kind of technique again. So I do think it's valuable to go through these lemmas, but if not, I'll see you in 2 videos. First, let's recall the actual definition of the outer measure. We define this for any subset of the full omega, so not just sets in the sigma field. And we called it P star, and P star of A was the smallest of the sum of the probabilities, which you can think of as areas, of all the sets covering A. And you saw in the previous slide that we covered a set A and we had sets that overlapped each other. So if we're adding the individual probabilities, we're going to have, extra probability. We're not finding the probability of the union, we're adding them all up. So we're getting all the overlap. And the sets also went outside the original set. So we're getting that extra measure. And so we want to try to make this total probability as small as possible, hence the infimum, which is taken over all possible coverings of the original set A, where the covering sets come from F naught, the field in which P is defined. In the last video, we showed that this is in fact a probability measure on the measurable space omega curly F, F being the sigma field generated by F naught. We also showed that it preserved the original probability measure when you plugged in sets in the original F naught. That is, P star of A is equal to P of A if A is in the original F naught. So again, the point of this video is to prove the lemmas that we used. And so going forward today, you can't use the fact that P star is a probability measure. So you can't use properties of a probability measure because these are the lemmas we needed to get that result in the last video. So we don't know that at this stage. Our proofs did involve a collection of sets that we called this capital curly M. And these are all the subsets A of omega for which P star A intersect B plus P star A complement intersect B is equal to P star of B for any B subset of omega. Now, this is the countable additivity property, which should hold if P star is in fact a probability measure, but we don't know that it is. And whether or not it holds will actually depend on the sets we look at. And so that's what this collection is. It's the collection where that property does hold. Now, even though we don't have countable additivity because we don't know that P star is a probability measure, we did have 4 or 5 properties like 2 videos ago for P star. One of them was a countable subadditivity result. So if you break up a set B into the part that intersects with A and the part that intersects with A complement, we can say that P star of B is less than or equal to the sum of the two parts, to the sum of P star of A intersect B plus A complement intersect B, which means we already have part of this equality. We have an inequality. And so if we can prove the other part of the inequality, then that is how we can characterize sets in M. So we can define M in one of 2 ways. And the reason these are equivalent is because this inequality in reverse already holds by countable subadditivity of P star. By the way, this collection M is going to be a collection on which we have that P star is a probability measure. And since we're kind of getting them from the P star, these are called, the sets in this collection are called P star measurable sets, but you don't need to know that for anything. So let's prove our first 3 lemmas. Lemma 1 is that this collection is a field. So to show this, we have to show 3 things. There was an I, double I, and triple I. The first property is we want to show that the full omega is in M, or equivalently that the empty set is in M, because the second property is going to be that it's closed under complements. So if you show the empty set is in M, then omega will be in M and vice versa. But I'm going to stick with omega. So what is the definition of sets in M? What does it mean to be included in M? It means that for any B subset of omega, if we look at P star of omega intersect B plus P star of omega complement intersect B, we want this to equal P star of B if we truly have that omega is in M. So let's just simplify these 2 probabilities. Omega intersect B is, of course, B, and omega complement being the empty set intersected with B is the empty set. We did show a couple of videos ago in the properties before we started talking about whether or not P star was a probability measure, that P star of the empty set is in fact 0. Again, that's something that's always expected of a probability measure, but at this point, we don't know that it's a probability measure. However, we did prove that P star of the empty set is 0. So we end up with P star of B. And so this part equaling this part means that omega is included in M, and that's what we wanted to show. For the second step, we want to show that M is closed under complements. That is, we want to take a set A in M, and if A is in M, we want to show that the complement has to be in M. But this is clear by the symmetry in the definition of M, because if A is in M, that means for any B subset of omega, P star of A intersect B plus P star of A complement intersect B is equal to P star of B. But you can just flip these terms around, and this is the same thing as saying P star of A complement intersect B plus P star of A, which is A complement intersect B, is equal to P star of B. I mean, we get this from the line above, and this is the line that tells us that A complement is included in the collection of sets curly M. So the third thing we have to show is going to take a little more work than both of these. This is where we want to show, and remember, this is just, we're showing it's a field, not a sigma field, although it is, we'll show that later. But we want to take a finite collection of sets in M. So I want to remind you, they don't need to be disjoint. The only time you need disjointness is when we're talking about the measures adding up. I'm just going to take a finite collection of sets in M, disjoint or not. And we want to show that the union, this finite union, is again in M. So let's look at it for n equals 2. Let's take an A1 and an A2 in M and show that A1 union A2 is in M. Now, this is actually easier if we show it for the intersection. And if we can show it for the intersection, how will this give us the result we actually want? The A1 and A2 being in M means that A1 complement and A2 complement are in M from step 2 in our proof. And if we show that the intersection of elements of M is in M, this means that A1 complement intersect A2 complement is in M. And because the complement of anything in M is in M, this means that A1 complement intersect A2 complement, all complemented is in M, but all of that gives you A1 union A2. So this argument I just made here assumes that M is closed under intersections to get that M is closed under unions. So let's show that it's closed under intersections, which I think is the easier of the two, just given the nature of how M is defined with intersections in the defining criterion. Okay, so let's go take an A1 and A2 in M, and we want to show that A1 intersect A2 is in M. And what does it mean for that new set to be in M? This is the defining criterion for a set like A1 intersect A2 to be in M, or equivalently, we could change out this equal sign with a less than or equal to. And this has to hold for any subset B of omega. So I want to look at the left-hand side here and hopefully get to the right-hand side. Take any B, again, subset of omega, and here's the left-hand side. The first thing I want to do is rewrite this. So the first term is an intersection intersected with something else. That's just a three-way intersection. So I can rewrite the intersection of A1 and A2, like close parentheses, intersected with B, as just the intersection of A1, A2, and B. The second term I can write in many ways, and I want to write it in a way that is useful for our goal of proving that the intersection is in M. Let's take a look at the set in here. I want everything that is in B and outside of the intersection of A1 and A2. So if I shade that, the region looks like this. And I can break this up into disjoint regions like this. And let me describe these with unions and complements and intersections. So I am going to rewrite the space here where I have a question mark as hopefully a sum of three different terms, but I'm not going to go there yet. I want to write it as a P star of a union of three terms. Now, by just observing this diagram, this yellow part is everything that is in A1 and not in A2, and also in B. So this yellow part can be written as A1 intersect A2 complement intersect B. And this green part over here is everything that's not in A1, not in A2, and in B. So we can write this green part as A1 complement intersect A2 complement intersect B. And finally, this kind of pinkish, reddish salmon part here, we can write this as everything that's outside of A1 and inside of A2 and inside of B. So I have written this whole shaded region as a union of three pieces. And again, we don't know that P star is a probability measure. So I can't say by countable additivity that this is P star of this set plus P star of this set plus P star of this set. But we did prove that P star is countably subadditive. So I can replace this P star of this union of three big sets here. I don't know how big they are, but big expressions with the sum of the individual P stars, as long as I put a less than or equal to sign before I write the next line. So here it is. I've changed my equal sign to a less than or equal to, and I've distributed the P star across the union. Let's take a step back and think about what we're trying to show here. We're trying to show that this expression here is equal or less than or equal to, and I think that's where we're going with this one, to P star of B. In order to get to this P star of B, I want to combine two terms in this expression and then the other two terms so that I've changed my four terms into two terms. And I want to combine them in a way that's useful for me knowing the definition of what it means for a set to be in M. Recall again that this is how we define M, or an inequality. And if A1 is in M, which is our assumption starting this proof, then I can say that P star of A1 intersected with A2 complement intersected with B plus P star of A1 complement intersected with A2 complement intersected with B. So I can group these two terms in an intersection and these two terms. And now I have what looks like the definition of M. If A1 is in M, then A1 intersected with something and A1 complement intersected with something put into the two P stars needs to equal or be less than or equal to P star of this set. So in other words, I can combine the two terms, which are color-coded to match the previous slide, to one term that looks like this. Grabbing the other two color-coded terms from the last slide, if I know that A1 is in M, which is the assumption, then here I have P star of A1 intersected with a set plus P star of A1 complement intersected with the same set. And since A1 is in M, this is going to equal P star of the set A2 intersect B. Let's go back and plug this into what we had on the previous slide, which was this. I'm going to combine these two terms, and that's what we just did. And we end up with this. But wait, A2 is in M, right? We started with assume A1 and A2 are in M. So the sum of these two terms is equal to P star of B because A2 is in M. And so this is one of our two ways to show something is in M. And so starting from here, going all the way to here, we've got that this is less than or equal to this. And that means that this set is in fact included in M. And using the De Morgan's laws and the complements and the intersections and turning them into unions, we have ultimately showed that if you take two sets, A1 and A2 in M, the union is also in M. I'm only showing this here for n equals 2. I'm sure you realize that to show this really, really formally in mathematics, you would use an inductive argument. So you would show it's true for two sets, and then you would assume that it's true for unioning up maybe n sets. And using that assumption, you want to show that it's true for unioning up n plus 1 sets. But really, n plus 1 sets in a union is a union of n sets. That whole big union with another set. And it's really just a matter of unioning two sets at a time. So I think I made that sound harder than it had to be. Suppose you want to show it for three sets, A1, A2, A3. They're all in M. Then you know that the union of A1 and A2 are in M. And if the union of A1 and A2, if you call that, say, A4, now you have an A4 in M and your original A3 in M, and that union has to be in M. And we've shown that the union of two things is in M, so that will hold. And that's kind of formal, but a little bit informal for an inductive proof. And I'm leaving out the actual writing out those three steps of an inductive proof because it's kind of this is messy enough for a slide video environment. So I hope that makes sense. Next up, lemma 2. We want to show that countable additivity with P star holds for sets in M. So to prove this, I'm going to start with finite unions, and I will move on to countable unions because unlike going from 2 to 3 is not a big deal, going from finite to an infinitely countable set is kind of a big deal. So this is not a simplification, it's just a step towards what we really want. Let's let A1, A2 up through AN be disjoint sets from M. We want to show that P star of the union is equal to the sum of the individual P stars. Let's actually go for a slightly stronger result while we're here, because we're going to need this result later for something else. So let's take any subset B of omega, and let's try to show that P star of B intersected with the entire union of the A's is equal to the sum of P star of B intersected with each A individually. This is a stronger result and will give us what we actually want, which looks like this, if we take B to be the full omega. Let's show this by induction on N. Again, I'm going to be just a little bit loose with this because it makes the slides too messy to have it completely written out, but everything you need is here. When N is 1, this expression here becomes P star of B intersect A1 equals P star of B intersect A1. And those are definitely equal. So we've got the case where N equals 1. For N equals 2, which is usually not something you look at in induction, you assume it's true for like N equals some K, and then you prove it for K plus 1. But for N equals 2, what we want to show is that P star intersected with this union is equal to this expression here. Again, remember that A1 and A2 are disjoint. Let's look at the left-hand side. The left-hand side is P star of B intersected with the union of A1 and A2. Again, A1 and A2 are disjoint sets from M, and B is any subset of omega. I'm going to draw a Venn diagram. Now, it could be that B is disjoint from A1 or A2 or both, or it could be that B is completely contained in A2. We can have all sorts of relationships between these sets. In general, when you don't know anything, you want to at least give them a chance to intersect. And if that intersection is empty, so be it. But I do know that A1 and A2 are disjoint, so I am going to draw A1 and A2 that way. So B intersected with the union of A1 and A2 consists of these two pieces that are colored in here. I am going to write this intersection as this piece plus this piece. So I can take this entire set here and intersect it with A1, and then the entire set and intersect it with A2, and that will give me the two pieces I want. I can, in fact, say that this is equal to this. Now, it looks like I have used countable additivity of P star, and at this point, we do not know that P star is a probability measure, and we do not have countable additivity. However, this is equal to this by definition of A1 being in M. Remember, A1 is in M. If you take any subset of omega, if P star of A1 intersect that set, plus P star of A1 complement intersect that set is equal to P star of that set. So that's what's going on here. I'm not using countable additivity. Now let's look at the picture to rewrite this. This set here consists of these two pieces, and if I intersect with A1, I just get this piece, which can be rewritten as A1 intersect B. Now this piece over here is equivalent to intersecting A2 with B, so I'm going to write that. And this from here to here is what we wanted. We have shown the slightly stronger result than the countable additivity, where we included this set B, but this is the result that we wanted to show when n is 2, when we're looking at two subsets or two elements of M. We are still in step 1 of this proof, where we're trying to show this result for finite unions. And so if you can show it for 2, then you can show it for 3. And if you want the more formal inductive step that I keep skipping, what you need to do is replace this union with a big fat union of n plus 1 A sets, and replace this A1 with a big fat union of only n of the A sets, and let A2 be the A n plus 1, because the union of this and this gives you this. And so you can write the exact proof I had on the previous slide with these sets in place of the A1 and A2. And that's how you'll prove it more formally. But again, that's a little messy for the slides, and that's why I'm not doing it. It's time to move on to step 2. We want to go from P star is finitely additive on the set of collection of sets M to countably additive. So we want to show that if we take an A1, A2, et cetera, a countable collection of disjoint sets from M, we want to show that the P star of the union is equal to the sum of the P stars, but we are going for this stronger result that involves intersecting the whole thing with B. So let's look at P star of B intersected with the infinite but countable union. Just draw yourself some Venn diagrams to convince yourself that you can kind of distribute this intersection across the union like this. It's easy to see if you draw the circles. Now we do have that P star is countably subadditive, so disjoint or not, the P star of this union is less than or equal to the sum of the individual P stars. And this equaling this is what we want to show, and we have that it's less than or equal to. So now let's show the other inequality. Let's start again by distributing the intersection of B throughout the union. Here's where we're going to use step 1. We do know something about this if this was a finite number. Note that if I make it a finite number like n, that I have a smaller set potentially. And so we did show in the original properties of P star that if you have like an A subset of B, then P star of A is less than or equal to P star of B. So we do have that kind of monotonicity property that allows us to say that the P star of this union is actually larger than the P star of what is potentially a smaller union. And this holds for any n. And now we can use the finite additivity from step 1 to rewrite this as the sum of the P stars of the individual intersections. So we get that from the finite case. Okay, so I don't care about this finite n though. So check this out. We have shown that P star of this expression is greater than or equal to the sum up to n of this expression. I'm going to take the limit as n goes to infinity on both sides of this inequality. Now you'll notice there's no n over here, and that's okay. The limit as n goes to infinity of the number 3 is the number 3. It's just staying constant. So when I take the limit on the left-hand side, I just get the left-hand side because, again, there's no n there. When I take the limit as n goes to infinity on the right-hand side, that's how we define an infinite sum. We start with partial sums like this and take the limit. So when taking the limit on both sides as n goes to infinity, this line turns into this line. Now we're still in step 2. On the other hand, we have the result, the on the other hand result, that this is greater than or equal to this. And yet when we started step 2, we showed that this is less than or equal to this. Put those together and we have that this is equal to this as desired. That concludes our proof of lemma 2, that P star satisfies countable additivity for sets in M. Lemma 3, our final lemma for this video, we want to prove that M is a sigma field. And why didn't we do that in lemma 1? Well, lemma 1 is actually a lemma for lemma 3. It's part of it, and we're breaking things down into manageable steps. So to show it's a sigma field, we have to show 3 things. 2 of those things already hold because we showed that M is a field in lemma 1. What we need to show is that M is closed under countable unions. We're not working with a measure here, so we don't need to be talking about disjoint sets, but we want to show that countable unions of sets in M are in M. I'm going to take a bunch of sets in M. Again, they don't have to be disjoint, A1, A2, etc. And I'm going to union them all up. And that new set, I'm going to call it A. I am going to assume that the AN are disjoint. They're probably not disjoint. But the reason I can assume this is because if they are not disjoint, you can form the sets B1, B2, B3 like this. You can let B1 be A1. And you can let B2 be everything that's in A2 but out of A1. So definitely disjoint from the first set. And you can let B3 be everything that's in A3 but outside of A1 and outside of A2. So B3 is disjoint from B2 and B1. And what I'm forming here is a sequence of disjoint sets. But if you union them, you will get the union of the original non-disjoint, potentially non-disjoint sets. It's like, imagine a union of, say, 3 sets, and we're putting it together by taking all of the first set and then taking part of the second set that's not in the first set and then taking the remaining part of the third set. And so the original union can be written as a union of disjoint pieces. And so I could have said this and then proved the result with the B's. But to make the proof a little more streamlined, I'm just going to say, assume the A's are disjoint. If not, then do this trick. If we can show the union of the B's is in M, then we have that the union of A's is in M, even if the A's are not disjoint. But again, I'm just going to assume that the A's are disjoint. And I'm going to define a set CM to be the finite union as n goes from 1 up to M of the AN. Since M is a field, by lemma 1, we do know that this finite union is in M. And that means, using one of our 2 criteria for inclusion in M, that P star of B is equal to P star of CM intersect B plus P star of CM complement intersect B for any B subset of omega. Let's look at these individual terms a little more closely. The first one, P star of CM intersect B. CM is just this finite union, and I'm going to just fill that in. That's all I'm doing. This is the definition of CM. And we can distribute this union and intersection. We've done this before, but convince yourself by drawing some pictures, drawing some Venn diagrams. Now, we do know that by lemma 2, that P star satisfies countable additivity, which includes finite additivity in M. And that result did require disjoint sets. But here I'm assuming the AN are disjoint. And if you take a bunch of disjoint sets and intersect them with something, then the results are still going to be disjoint. So these are disjoint sets. P star satisfies countable additivity and therefore finite additivity. So we can take this union inside and turn it into a sum outside by lemma 2. Let's look at the other term. Now CM is the finite union here, and our set A was the infinite union. So this finite union is contained in the infinite union. In other words, or in other symbols, CM is contained in A. And so if you complement things, that means the containment is going the other way around. So A complement is contained in CM complement. So A complement is a set, and it's contained in another set that we're calling CM complement. And if we intersect A complement with B, we're going to get some part of what we would get if we intersected the larger set CM complement with B. In other words, A complement intersect B is contained in CM complement intersect B. We did have the monotonicity property of P star shown several videos ago before we even started the lemmas. So we can say that P star of this set is less than or equal to P star of this set. So I have rewritten this first set with an equality, and I have bounded this set above with something. So plugging in what we had for this expression and bounding this below by this term, we have that P star of B is greater than or equal to a sum of two things now. Let's let M go to infinity on both sides. This term and this term are constants in M, so they just go unchanged, but this term turns into an infinite sum. By lemma 2, P star is countably additive for sets in M. So what I kind of want to do is take this sum out here and turn it into a union on the inside. But I don't know that even though the ANs come from M, I don't know that AN intersect B is in M. So I can't do this. What I can do is use countable subadditivity of P star to say that the P star of a union is less than or equal to the sum of the P stars. So in other words, going backwards, this sum is greater than or equal to P star of the union. We can pull the union inside and rewrite this as this set in here as the union of the ANs, total, parentheses, intersected with B. But the union of the ANs, the infinite union, is what we're calling A. So this is P star of A intersect B plus P star of A complement intersect B. And we've just shown that P star of B is greater than or equal to P star of A intersect B plus P star of A complement intersect B. And that is one of our two criteria for saying that the set A, which is the infinite union, is in M. So we have shown it. We started with a collection of sets, A1, A2, et cetera, in M. We assumed they were disjoint because if not, we could rewrite things so that they are. And we just showed that the countably infinite union is again in M. And when you combine this with lemma 1, that M is a field, we have just shown that M is a sigma field, thereby proving lemma 3. So that's all for today. In the next video, we're going to prove lemmas 4, 5, and 6. And then a video after that, if you're choosing to skip this, we're going to talk about limits of sequences of sets. So you might know what the limit of a sequence of numbers is, but what if you're talking about sequences of sets and you're trying to take a limit? What does that even mean? Stay tuned.